What's up, Crypto Nation? This is the Data Lord. Today we're going to be reading the Tezos white paper. Tezos is a pretty interesting project I actually think stands out amongst the crowd. It doesn't have a lot of hype behind it just yet, but I've done a lot of due diligence on different cryptocurrency projects, and Tezos, I think, is solving some problems that a lot of other blockchains aren't looking at the same way. And so I'm personally working on developing some tooling on Tezos currently, and I'll come out public about exactly what the tools are when they're ready to be shared out of just our early development cycle. So let's get into this. Let's read the white paper. So Tezos white paper. Introduction. In the first part of this paper, we will discuss the concept of an abstract blockchain. The first part of this paper, we will discuss the concept of abstract blockchains and the implementation of a self-amending crypto ledger. In the second part, we will describe the proposed seed protocol. Self-amending crypto ledger. A blockchain protocol can be decomposed into three distinct protocols. The network protocol discovers blocks and broadcasts transactions. The transaction protocol specifies what makes a transaction valid. And the consensus protocol forms consensus around a unique chain. Tezos implements a generic network shell. This shell is agnostic to the transaction protocol and to the consensus protocol. We refer to the transaction protocol and the consensus protocol together as a blockchain protocol. We will first give a mathematical representation of a blockchain protocol and then describe some of the implementation choices in Tezos. So, mathematical representation. A blockchain protocol is fundamentally a monadic implementation of concurrent mutations of a global state. This is achieved by defining blocks as operators acting on this global state. The free monoid of blocks acting on the genesis state forms a tree structure. A global canonical state is defined as the minimal leaf for a specified ordering. This suggests the following abstract representation. And I won't read that. I'll just let you look at it. Be a total ordered countable set of possible states. Represents a specific invalid state. And then this right here. Be the set of blocks. The set of valid blocks is this. The total order of this is extended so that this is just the math. It doesn't read very well if you speak it out loud. This order determines which leaf in the block tree is considered to be the canonical one. So, blocks are seen as operators acting on the state. All in all, any blockchain protocol, be it Bitcoin, Litecoin, Peercoin, Ethereum, CryptoNote, etc., can be fully determined by the tuple. And here's another equation. So the network protocol is fundamentally identical for these blockchains. Mining algorithms are but an emergent property of the network given the incentives for block creation. In Tezos, we make a blockchain protocol introspective by letting blocks act on the protocol itself. We can then express these set of protocols recursively. The network shell. This formal mathematical description does not tell us how to build the block tree. This is the role of the network shell, which acts as an interface between a gossip network and the protocol. The network shell works by maintaining the best chain known to the client It is aware of these three types of objects. The first two are transactions are blocks, which are only propagated through the network if deemed valid. The third are protocols. OCaml modules used to amend the existing protocol. They will be described in more detail later on. For now, we will focus on transactions and blocks. The most arduous part of the network shell is to protect nodes against denial of service attacks. Clock. Every block carries a timestamp visible to the network shell. Blocks that appear to come from the future are buffered if their timestamps are within a few minutes of the system time and rejected otherwise. The protocol design must tolerate reasonable clock drifts in the client and must assume the timestamps can be falsified. Chain selection algorithm. The shell maintains a single chain rather than a full tree of blocks. This chain is only overwritten if the client becomes aware of a strictly better chain. Maintaining a tree would be a more parsimonious in terms of network communications, but would be susceptible to denial of service attacks where an attacker produces a large number of low-scoring but valid forks. Yet, it remains possible for a node to lie about the score of a given chain, a lie that the client may only uncover after having processed a potentially large number of blocks. However, such a node can be subsequently ignored. Fortunately, a protocol can have the property that low scoring chains exhibit a low rate of block creation. Thus, the client would only consider a few blocks of a weak fork before concluding that the announced score was a lie. Network level defense. In addition, the shell is defensive. It attempts to connect to many peers across various IP ranges. It detects disconnected peers and bans malicious nodes. To protect against certain denial of service attacks, the protocol provides the shell with context-dependent bounds on the size of the blocks and transactions. Functional representation. We can efficiently capture almost all the genericity of our abstract blockchain structures with the following OCaml types. To begin with, a block header is defined as type raw block header equals predetermined block hash.t, header bytes.t, operations operation hash.t list, timestamp float. We are purposefully not typing the header field more strongly so it can represent arbitrary content. However, we do type the fields necessary to the operation of the shell. These include the hash of the preceding block, a list of operation hashes, and timestamp. In practice, the operations included in a block are transmitted along with the blocks at the network level. Operations themselves are represented as arbitrary blobs. Type raw operation equals bytes.t. The state is represented with the help of a context module, which encapsulates a disk-based immutable key value store. The structure of a key value store is versatile and allows us to efficiently represent a wide variety of states. Module context equals signature, type T, type key equals string list, and then I'm not going to read that, won't read well. You can look at it if you want to see the code there. To avoid blocking on disk operations, the functions use the asynchronous monad LWT bracket at LWT and bracket. Note that the operations on the context are purely functional. get uses the option monad rather than throwing an exception, while set and delete both return a new context. The context module uses a combination of memory caching and disk storage to efficiently provide the appearance of an immutable store. We can now define the module type of an arbitrary blockchain protocol. And this might not read well, but type score equals byte.t list, module type protocol equals sig, type operation, value parse block header, raw block header option. Yeah, I'm not going to read that. It doesn't read well. We no longer compare states directly as the mathematical model. Instead, we project the context onto a list of bytes using the score function. List of bytes are ordered first by length, then by lexicographic order. This is a fairly generic structure, similar to the one used in software versioning, which is quite versatile in representing various orderings. Why not define a comparison function within the protocol modules? First off, it'd be hard to enforce the requirement that such a function represents a total order. The score projection always verifies this. Ties can be broken based on the hash of the last block. Second, in principle, we need the ability to compare states across distinct protocols. Specific protocol amendment rules are likely to make this extremely unlikely to ever happen, but the network shell does not know that. The operations parse block header and parse operation are exposed to the shell and allow it to pass fully typed operations and blocks to the protocol, but also to check whether these operations are blocks and blocks are well formed before deciding to relay operations or to add blocks to the local block tree database. The apply function is the heart of the protocol. When it is passed a block header and the associated list of operations, it computes the changes made to the context and returns a modified copy. Internally, only the difference is stored as in a versioning system using the block hash as a version handle. When it only passed a list of operations, it greedily attempts to apply as many operations as possible. This function is not necessary for the protocol itself, but is of great use to miners attempting to form valid blocks. Amending the protocol. Tezos' most powerful feature is its ability to implement protocol capable of self-amendment. This is key, guys. This is key. This is achieved by exposing two procedure functions to the protocol. Set test protocol, which replaces the protocol used in the testnet with a new protocol, typically one that has been adopted through a stakeholder voter. And promote test protocol, which replaces the current protocol with the protocol currently being tested. These functions transform a context by changing the associated protocol. The new protocol takes effect when the following block is applied to the chain. I won't read that, it doesn't read well. The protocol hash is the SHA-256 hash of a tarball of .ml and .mli files. These files are compiled on the fly. They have access to small standard library, but are sandboxed and may not make any system call. These functions are called through the apply function of the protocol, which returns the new context. Many conditions can trigger a change of protocol. In its simplest version, a stakeholder vote triggers a change of protocol. More complicated rules can be progressively voted in. For instance, if the stakeholder desires that they may pass an amendment that will require further amendments to provide a computer checkable proof that the new amendment respects certain properties. This is effectively the algorithmic check of constitutionality. Pretty cool, yeah? Basically, people can vote if they're mining blocks, and if they vote on changes, it goes into a process where it goes to testnet, and then it goes into the actual amended block. It goes to the main blockchain. So there's no forking on Tezos. It's really cool. It's able to upgrade without being so dramatic. So, yeah. Let's do it. RPC. You're going to see this in most blockchains. It's a remote procedure call. It's basically kind of similar to like an API. It's like a standard protocol by which the application can grab data from the blockchain. So, in order to make the graphical user interface building jobs easier, the protocol exposes a JSON RPC API. The API itself is described by a JSON schema indicating the types of various procedures. Typically, functions such as getBalance can be implemented in an RPC. So, I want to talk about this for a second. So, JSON, for anyone who's just trying to understand what people are even talking about. So, JSON is a standard for forms. So a lot of websites typically use this. It's very, very common. So basically it'll list like, all of the different values and what their state is. So it'll look up, like, for example, like if you look up a wallet address, it would say balance equals 43 Tezos or whatever. So you would just see a list of all the values that are stored on that blockchain for that one value. So if you were to get the value being the wallet, it would give you all the details of that wallet in a standard way that you can have an application parse the data. So it's pretty easy to kind of pull data and then say, hey, I actually want this little bit here that's always going to be in this format to be stored in this other variable and displayed on my web page, for example. So that's a very practical reason why we would be using JSON. And then remote procedure calls are also another standard that are used across blockchain, and not just blockchain uniquely, but you will see it across blockchain. And then an API is an application programming interface. So that's like a standard way the application will share data, right? Some things are public, but other times you actually need a key in order to get certain types of data from an API. So let's continue. I hope that explanation's useful. The name is a list of string to allow namespace in the procedures. Input and output are optionally described by a JSON schema. Note that the call is made on a given context, which is typically a recent ancestor of the highest scoring leaf. For instance, querying the context 6 blocks above the highest scoring leaf displays the state of the ledger with 6 confirmations. The UI itself can be tailored to a specific version of the protocol or generically derived from the JSON specification. Seed protocol. Much like blockchains start with a genesis hash, Tezos starts with a seed protocol. This protocol can be amended to reflect virtually any blockchain-based algorithm. How cool is that? Economy. Coins. We suggest that a simple coin be referred to as a Tez, and that the smallest unit simply as a cent. We also suggest to use the symbol TZ, they give you the UA code for it. It's the Latin small letter TZ to represent a Tez. During the fundraiser, a total of 763 million, I won't read the rest of it, Tezos were generated and distributed to contributors to the fundraiser. Mining and signing rewards. Principle. We conjecture that the security of any decentralized currency requires to incentivize the participants with a pecuniary reward, as explained in the position paper, relying on the transaction cost alone suffers from a tragedy of the commons. In Tezos, we rely on a combination of a bond and a reward. Bonds are 5-cycle security deposits purchased by miners and endorsers. In the event of double signing, these bonds are forfeited. After a cycle, the miners and endorsers receive a reward along with their bond to compensate for their opportunity cost. The security is primarily being provided by the value of the bond, and the reward need only be a small percentage of that value. The purpose of the bond is to diminish the amount of reward needed, and perhaps to use the loss aversion effect to the network's advantage. Specifics. In the seed protocol, a mining block offers a reward of 16 Tez and requires a bond of 512 Tez per block created. Signing a block offers a reward of up to 2 Tez depending on the priority of the block which was created. There are up to 32 signatures per block, and signing requires a bond of 64 Tez. The reward schedule implies at most a 5.5 nominal inflation rate. Nominal inflation is neutral. It neither enriches nor impoverishes anyone. Note that the period of a year is determined from the block's timestamp, not the number of blocks. This is to remove uncertainty as to the length of the commitment made by the miners. Lost coins. If an address is inactive, it will not be selected to create blocks, which would slow down the consensus algorithm, and it would not be allowed to vote until it's reactivated to avoid uncertainty about participation rate. Amendment rules. Amendments are adopted over election cycles lasting $n equals 2 to the power of 17 equals, I'm not going to read that, blocks each. Given the a-minute block interval, this is about 3 calendar months. The election cycle is itself divided in 4 quarters. The cycle is relatively short to encourage early improvements, but it is expected that further amendments will increase the length of the cycle. Protocol upgrades votes will be much more frequent in the first year in order to allow for rapid iteration. As security measure, the Tezos Foundation will have the veto power expiring after 12 months until we rule out any kinks in the voting procedure. Adoption requires a certain quorum to be met. The quorum starts at quorum equals 80 divided by $, but dynamically adapts to reflect the average participation. This is necessary if only to deal with lost coins. So pretty cool. It actually incentivizes people to be actively involved in saying that they do or don't want certain things to be applied to the blockchain. So it kind of like they actively want to incentivize people to be guiding the destiny of Tezos. So it's cool. It's not like it's very democratic in how it's approached. First quarter. Protocol amendments are suggested by submitting the hash retarball of .ml and .mli files representing a new protocol. Stakeholders may approve of any of these protocols. This is known as approval voting, a particularly robust voting voting procedure. Second quarter. The amendment receiving the most approval in the first quarter is now subject to a vote. Stakeholders may cast a vote for, against, or can choose to explicitly abstain. Abstentions count towards the quorum. Third quarter. If the quorum is met, including explicit abstentions, and the amendment receives, I'm not going to read that, of yeas, the amendment is approved and replaces the test protocol. Otherwise, it is rejected, assuming the quorum reached was $Q$. The minimum quorum $Q$ is updated as such. The goal of this update is to avoid lost coins, causing the voting procedure to become stuck over time. The minimum quorum is an exponential moving average of the quorum reached over each previous election. Fourth quarter. Assuming the amendment was approved, it will have been running in testnet since the beginning of the third quarter. The stakeholders vote a second time to confirm they wish to promote the test protocol to the main protocol. This also requires the quorum to be met in 80% supermajority. We deliberately chose a conservative approach to amendments. However, stakeholders are free to adopt amendments, loosening or tightening the policy should they deem it beneficial. How cool is that? Proof of stake mechanism. So, overview. Our proof of stake mechanism is a mix of several ideas, including slasher, chain of activity, and proof of burn. The following is a brief overview of the algorithm, the components of which are explained in more details below. Each block is mined by a random stakeholder, the miner, and includes multiple signatures of the previous block provided by a random stakeholder, the signers. Mining and signing both offer a small reward, but also require making a 5-cycle safety deposit to be forfeited in the event of double mining or double signing. The protocol unfolds in cycles of 4,096 blocks. At the beginning of each cycle, a random seed is derived from numbers that block miners chose and committed to the penultimate cycle and revealed in the last. Using this random seed, a follow the coin strategy is used to allocate mining rights and signing rights to a specific address or to a specific addresses for the next cycle. 4 cycles of the proof of stake mechanism. Gotta fix this 1 second. Whee! This scaled like crap. Please forgive me. Yikes on bikes. I got this. We'll do it live. Just want to say, for anyone who's watching this, you guys are freaking OGs. This is cool. You guys are hungry for the good stuff, and I appreciate that. My goal is to make sure that I can help everyone be as successful as possible. No need to go this road alone, right? But anyways, yeah, you should be able to see here that basically you have a very clear setup of 2,048 blocks. There's 4 cycles though, so the secret numbers from previous cycles revealed in the first cycle, random seeds derived from all of the reveals for use in the third cycle at the end of that first cycle's block. And then you have safety bonds deposited for use in the third cycle in that first block. And then selected stakeholders who made a safety deposit mine and sign the chain and commit to secret numbers with a hash. And then secret numbers from the previous cycle are revealed on the fourth cycle. So it's pretty hard to pwn this thing, man. It's pretty robust, honestly. Yeah. I'm gonna make this look pretty again. Man. Whee! That'll do. Clock. The protocol imposes minimum delays between blocks. In principle, each block can be mined by any stakeholder. However, for a given block, each stakeholder is subject to a random minimum delay. The stakeholder receives the highest priority may mine the block 1 minute after the previous block. Stakeholders receiving the second highest priority may mine the block 2 minutes after the previous block, the third 3 minutes, and so on. This guarantees that a fork, where only a small fraction of stakeholders contribute, will exhibit a low rate of block creation. If this weren't the case, a CPU denial of service attacks would be possible by tricking nodes into verifying a very long chain claimed to have a very high score. So generating the random seed. Every block mined carries a hash commitment to a random number chosen by the miner. These numbers may be revealed in the next cycle under penalty of forfeiting the safety bond. This harsh penalty is meant to prevent selecting withholding of the numbers, which could be sued to attack the entropy of the seed. Malicious miners in the next cycle could attempt to censor such reveals. However, since multiple numbers may be revealed in a single block, they are very unlikely to succeed. All the revealed numbers in a cycle are combined in a hash list, and the seed is derived from the root using the script key derivation function. The key derivation should be tuned so that deriving the seed takes on the order of a fraction of a percent of the average validation time for a block on a typical desktop PC. The following coin procedure. In order to randomly select a stakeholder, we use the following coin procedure. Principle. The idea is known in Bitcoin as follow the Satoshi. The procedures works as if every Satoshi ever minted had a unique serial number. Satoshis are implicitly ordered by creation time. A random Satoshi is drawn and tracked through the blockchain. Oh my goodness, let's go. I'm into this. I've been up for a while. Instead, rules are applied to describe what happens when the inputs are combined and spent over multiple output. In the end, the algorithm keeps track of a set of intervals associated with each key. Each interval represents a range of Satoshis. Unfortunately, over time, the database becomes more and more fragmented, increasing bloat on the client side. Coin rolls. We optimize the previous algorithm by constructing large coin rolls made up of Tez. There are thus about 1 million rolls in existence. A database maps every roll to its current owner. Each address holds a certain set of specific rolls as well as some loose change. When we desire to spend a fraction of a full roll, the roll is broken and its serial number is sent in a LIFO queue of rolls, a sort of limbo. Every transaction is processed in a way that minimizes the number of broken rolls. Whenever an address holds enough coins to form a roll, a serial number is pulled from the queue and the roll is formed again. The LIFO priority ensures that an attacker working on a secret fork cannot change the coins he holds by shuffling change between accounts. A slight drawback of this approach is that stake is rounded down to the nearest integer number of rolls. However, this provides a massive improvement in efficiency over the follow the Satoshi approach. While the rolls are numbered, this approach does not preclude the use of fungibility preserving protocols like zero cash. Such protocols can use the same limbo queue technique. Motivation. This procedure is functionally different from merely drawing a random address weighted by balance. Indeed, in a secretive fork, a miner could attempt to control the generation of random seed and to assign it itself signing and minting rights by creating the appropriate addresses ahead of time. This is much harder to achieve if roles are randomly selected, as the secretive fork cannot fake ownership of certain roles and must thus try to pre-image the hash function applied to the seed to assign itself signing and minting rights. Indeed, in a cycle of length, I won't read that. It's just saying 2048 cycle, or was it? Yeah, blocks. Someone holding a fraction of the rolls will receive, on average, n mining rights, and the effective fraction received, with a standard derivation. If an attacker can perform a brute force search through W different seeds, then this expected advantage is at most, and it gives an equation I'm not going to read. For instance, an attacker controlling 10% of the rolls should expect to mine about 205 blocks per cycle. In a secret fork where he attempts to control the seed, assuming he computed over a trillion hashes, he could assign itself about 302 blocks, or about 14.7% of the blocks. Note that the hash from which the seed is derived is an expensive key derivation function, rendering brute force search impractical. To make linear gains in blocks mined, the attacker needs to expend a quadratically exponential effort. Mining blocks. The random seed is used to repeatedly select a roll. The first roll selected allows its stakeholders to mine a block after 1 minute, the second one after 2 minutes, and so on. When a stakeholder observes the seed and realizes he can mint a high priority block in the next cycle, he can make a security deposit to avoid a potential problematic situation where no stakeholder made a safety deposit to mine a particular block. After a 16-minute delay, the block may be mined without a deposit. Bonds are implicitly returned to their buyer immediately in any chain where they do not mine the block. Signing blocks. As it is, we almost have a working proof-of-stake system. We could define a chain's weight to be the number of blocks. However, this would open the door to a form of selfish mining. We thus introduce a signing scheme. While a block is being minted, the random seed is used to randomly assign 32 signing rights to 32 rolls. The stakeholder who received signing rights observe the blocks being minted and then submit signatures of the blocks. Those signatures are then included in the next block by miners attempting to secure their parents' inclusion in the blockchain. The signing reward received by signers is dependent on the priority of the miner who mined the block. The higher the priority, the higher the signing reward. Signer thus have a strong incentive to sign what they genuinely believe to be the best block produced in one point. They also have a strong incentive to agree on which block they will sign, as signing rewards are only paid if the block ends up included in the blockchain. If the highest priority block isn't mined, perhaps because the miner isn't online, There could be an incentive for signers to wait for a while, just in case the miner is late. However, other signers may then decide to sign the best priority block, and a new block could include those signatures, leaving out the holdouts. Thus, miners are unlikely to follow this strategy. Conversely, we could imagine an equilibrium where signers panic and start signing the first block they see for fear that other signers will do so, and that a new block will be built immediately. This is, however, a very contrived situation which benefits no one. There is no incentive for signers to think this equilibrium is likely, let alone to modify the code in their program to act this way. A malicious stakeholder attempts to disrupt the operations would only hurt itself by attempting to follow this strategy, as others would be unlikely to follow suit. Weight of chain. The weight is the number of signatures. Denunciations. In order to avoid the double minting of a block or the double signing of a block, a miner may include in his block a denunciation. This denunciation takes the form of two signatures, each minting signature or block signature signs the height of the block, making the proof of malfeasance quite concise. While we could allow anyone to denounce malfeasance, there is really no point to allow anyone else beyond the block miner. Indeed, a miner can simply copy any proof of malfeasance and pass it off as its own discovery. Once a party has been found guilty of double minting or double signing, the safety bond is forfeited. Smart contracts. Contract type. In lieu of unspent outputs, Tezos uses stateful accounts. When those accounts specifically execute code, they are known more generally as contracts. Since an account is a type of contract, one with no executable code, we refer to both as contracts in full generality. Each contract has a manager, which in the case of an account is simply the owner. If the contract is flagged as spendable, the manager may spend the funds associated with the contract. In addition, each contract may specify the hash of a public key used to sign or mine blocks in the proof of stake protocol. The private key may or may not be controlled by the manager. Formally, a contract is represented. I'm not going to read that. The handle of a contract is the hash of its initial content. Attempting to create a contract whose hash could collide with an existing contract is an invalid operation and cannot be included in a valid block. Note that the data is represented as the union type. When int is a signed 64-bit integer and string is an array of up to bytes, the storage capacity is limited to bytes, counting the integers as 8 bytes and strings as their length. Origination. The origination operation may be used to create a new contract. It specifies the code of a contract and the initial content of the contract storage. If the handle is already the handle of an existing contract, the origination is rejected. There's no reason for this to ever happen unless by mistake or malice. Transactions. A transaction is a message sent from one contract to another contract. This message is represented in this way. I'm not going to read that again. If you're interested, you can pause the video here. Such a transaction can be sent from a contract if signed using the manager's key, or can be sent programmatically by code executing in the contract. When the transaction is received, the amount is added to the destination's contract balance and the destination's contract code is executed. This code can make use of the parameters passed to it. It can read and write contracts storage and change the key or the signature key and post transactions to other accounts. The role of the counter is to prevent replay attacks. A transaction is only valid if the contract's counter is equal to the to the transactions counter. Once a transaction is applied, the counter increases by 1, preventing the transaction from being reused. The transaction also includes the block hash of a recent block that the client considers valid. If an attacker ever succeeds in forcing a long reorganization with a fork, he will be unable to include such transactions, making the fork obviously fake. This is a last line of defense. TAPOS is a great system to prevent long reorganizations, but not a very good system to prevent short-term double spending. The pair, account handle counter, is roughly the equivalent of an unspent output in Bitcoin. Storage fees. Since storage imposes a cost on the network, a minimum fee of 1 Tez is assessed for each byte increased in storage. For instance, if after the execution of a transaction an integer has been added to the storage and 10 characters have been appended to an existing string in storage, then 18 Tez will be withdrawn with the contract's balance and destroyed. Code. The language is stack-based with high-level data types and primitives and strict static type checking. Its design is inspired by Forth, Scheme, ML, and Cat. A full specification of the instruction set is available in @language. This specification gives the complete instruction set, type, system, semantics of the language. It is meant as precise reference manual, not an easy introduction. Fees. So far, the system is familiar to the way Ethereum handles transactions. However, we differ in the way we handle fees. Ethereum allows arbitrary long programs to execute by requiring a fee that increases linearly with the program's executing time. Unfortunately, while this does provide an incentive for one miner to verify the transaction, it does not provide such an incentive to other miners, who must also verify this transaction. In practice, most of the interesting programs that can be used for smart contracts are very short. Thus, we simplify the construction by imposing a hard cap on the number of steps we allow the program to run for. If the hard cap proves too tight for some programs, they can break the execution in multiple steps and use multiple transactions to execute fully. Since Tezos is amendable, this cap can be changed in the future, or advanced primitives can be introduced as new opcodes. If the account permits, the signature key may be changed by issuing a signed message requesting the change. Conclusion. We feel we've built an appealing seed protocol. However, Tezos' true potential lies in putting the stakeholders in charge of deciding on a protocol they feel best serves them. Now, I know that was a lot to take on, but do you see some of the points I was making? Like, Tezos specifically wants its community to be actively involved in validating and also in amending how they handle smart contracts, how they handle kind of everything. It's up for conversation. So they're specifically looking at some of the drawbacks from Ethereum and trying to improve on it. And so Tezos is super fast. It's always been proof of stake. Tezos is very, very amendable code. It follows a lot of best practices. It does support smart contracts. Obviously, it supports, payment systems. There's a lot to like here. It's referencing concepts from Bitcoin and Litecoin and Ethereum. And so keep in mind, I've gone over this a few times on DCTV. Bitcoin was the first cryptocurrency, right? And so Bitcoin kind of set some standards. Bitcoin was like, hey, we want there to be no middleman between a buyer and a seller, right? So if you give goods or services, we want you to be able just to give cash directly to that person and not have a banker or some broker arbitrage person in the middle. We'll just have code that stands in the middle, and the code executes as it's coded. It has no opinion or preference to or from one person to the other. So that was beautiful. We then saw some people say, hey, we could fork Bitcoin and we could maybe tweak the economics of it and whatnot and make something that's lower fees, a little faster. That's how Litecoin was kind of born. And then we started seeing people test out like, okay, well, what if we want to add more functionality? Like, what if we want to be able to make a smart contract where we can say like, hey, if this, then that with our money. And then Ethereum kind of popped up with that application, right? We then saw a whole bunch of altcoins pop up, and they're, again, experiments. They're testing parameters on in these core systems we've proven. And then Ethereum also popped up NFTs, non-fungible tokens, with their ERC 721, I believe. And then we see other platforms start supporting NFTs as well. So NFTs are basically certificates of authenticity, and they can be applied to art. Originally, that was the first use case, but they can be applied to anything. It's meant to be like a certificate of authenticity. And then we're seeing recently Vitalik started talking about soulbound tokens. So basically the idea is you have an NFT that's non-transferable. It's basically minted on one wallet and it stays there. And it's meant more for validating your identity. So my point is we have all of these different mechanisms in this ecosystem, and people are kind of tweaking little approaches to it and trying to see if it works the best. And I think Tezos is onto the right track, because Tezos didn't paint themselves into a corner. Tezos can be amended over time. Tezos doesn't have, big companies kind of behind them like you might see with some other platforms. Like Solana has a lot of people from Silicon Valley behind them. You have Ethereum has like the whole Ethereum alliance behind them, like Microsoft and some other companies. So I suppose my point is I feel good about Tezos because it's very democratic. Like people who are mining and helping support the network, they're given the ability to vote on where they do and don't want Tezos to go. I think that's really cool. So I have good feelings about Tezos and all of my due diligence, and I'll continue to share what's going on in the whole Tezos ecosystem, but pretty cool stuff. But keep in mind, all of these altcoins are experiments, right? And they should be treated as such. They should be treated as scientific hypotheses. And I think when you look at them as experiments, and some experiments are successful and stick around for a very long time, and that's great if that happens, right? But let's be constructive with people in their experiments, because even if you ever see an experiment that isn't successful, it still contributes to the body of knowledge that moves the space forward. So there's a lot of camaraderie in the cryptocurrency space for that reason. So I hope that's giving you some perspective. Thanks for hanging out with me while we read the white paper and talk it over a little bit. If you have any questions, the Tezos Discord community is pretty active. I've gotten some great answers from people in that Discord, so feel free to hop in there and get involved. I'm the Data Lord. Until next time.